Sorry about that, AP Calc. My program crapped out as soon as I clicked on the camera, which happens from time to time, you know? There's something going on with OBS that crashes when I activate a different window. So here we are. We're in the middle of this related rates problem. Hopefully we didn't lose too much. All we're really doing here is solving this Pythagorean theorem question for that diagonal there. So 200 squared plus 120 squared is that number, which might actually be a perfect square. Well, you know, we could only be so lucky. So it looks like the actual diagonal that is there is 233.238. That is the actual distance between the two cars at this moment in time. So that will go in the place of D in this equation over there, 233.238. And so honestly, this becomes a game of just do the algebra really quick. 200 times 40 plus 120 times 30 is this number. So what we're really looking for here is d dt is equal to 11,600 divided by 233.238. And it should make kind of a reasonable sense. We know one car is going 40 miles an hour, one car is going 30 miles an hour, so it should be like a pretty good, like, you know, some sort of diagonal change version of that number. So let's try it really quick. Let's see what we get. You know, 49 kind of fits. 49 miles an hour, I like it. 49.735. I got to round up, yeah. So it looks like we're getting 49.735. Yeah, we're going to round that up. Miles per hour is the unit on that one. There it is. Oh, let's get that out of the way. There you go. Nice work, everybody. That's pretty good. 3.238, yeah. Good. Good. Okay, let's go on to the next problem. I know that one would take a little bit of time. 741, we're going to write equations of tangent lines to a function that passes through the origin. So getting our tangent line practice of the day, 741. Let's go ahead and think about, this is 741 right here. Our equation is y equals x squared plus 2x plus 4. And we want to know the equation of a line tangent to that passes through the origin. So, first of all, let's figure out what the slope is. We're looking for the tangent line, tangent at 0, 0. This is going to be really easy because if you think about your point slope form, both of the x1 and y1 coordinates will be 0 and 0. So let's go ahead and take the derivative. We'll do y prime is going to be 2x plus 2. And we need to know what y prime is when x equals 0, and that is going to be just the number 2. So this is y minus 0 equals 2 times x minus 0, and that is, my friends, y equals 2x. And that's it. And you know, we even have time to graph it really quick here too, so to make sure you can see you're right. It will be x squared plus 2x plus 4 there, and then our line is 2x. And if we graph this on a standard window, we should see the parabola come through like that, and uh-oh. Uh-oh, I was so confident. What did I miss? What did I miss? Write the equation of the line tangent to that passes through the origin. Oh, the line has to pass through the origin. Oh, this question is way more complicated than I thought it was. I remove it. This is not a... Oops, sorry. This one's out. That one's out. That's a BC topic. That is not an AB topic. I mean, it's not too tough to do. What you have to do is you have to think about the... You know what the slope has to be. Oh, it's rough. This is a rough one. No, we're not doing 741. I misread that question. I apologize for the time that I took to even think about it. Let's look at 742. Kimberly and Vrog are in a bicycle race. If Kimberly's velocity in miles per hour during the race is that velocity function, calculate her average velocity during the span from 0 to 6 and describe your method. I'm going to get rid of my work for 742, 741 here, so I can look at 742. All right, so for part A here on 742, we are given a velocity function, and we're looking for the average velocity. So what we're going to do is we're going to use the integral version of the average velocity. That is just going to be 1 over 6 minus 0 times the integral from 0 to 6 of the velocity function, v of t dt. This is how you find the average when you're given the velocity and you want the average velocity. You got to use the integral version because they're kind of on the same level. Woof. I knew that would happen. We're going to let the calculator do this for us. Oh, there it is. Oof. Let's go back out to the main screen here. So we're going to have 1/6. I'm actually just going to erase this. Let's go ahead and multiply that times the integral. I got another one coming up. Whoa. I got it. I find int from 0 to 6. And the function here is 2.3 to the x power times the sine of 1 or x over 2. So it looks like the average velocity is about 16.102 miles per hour in this problem there. Oof. Now in question B, Virag's distance, this is distance. His distance from the starting line is given to us by this distance function, but we still want average velocity. So since now we have a distance graph and we want to know the average velocity, we have to think in terms of derivatives. But of course, I mean, we could take the derivative of s of t and do exactly what we just did in the previous problem. Or we could use the mean version of the average and just basically find the slope. What is s of 6 minus s of 0 over 6 minus 0? Whoops, I need a... So what is s of 6 minus s of 0 over 6 minus 0? Again, we'll let the calculator do most of the heavy lifting for us in this problem, but that's the calculation that we want to run. So we're doing 20 times 0 plus 2 times the sine of 0. Well, that's easy. I don't need a calculator for that, but I'm going to do it anyway. And then we have 20 times 6 plus 2 times the sine of 6. Is that right? Yeah, that'll not be 0, 119. So this is going to be 119.441 minus 0 over 6. And so we'll just divide those, divide it by 6, and get 19.907 miles per hour. So the difference in these two problems is that one of them is asking for the average velocity with the velocity function, in which case you want to use the integral version. But when you're given the distance and you want the average velocity, you got to go up a level and think about slope, average slope over time. When is each bicyclist traveling at his or her average velocity? This one we might want to go to the graphing calculator for, but the mean value theorem does say that it's going to happen at least once. So let's let the graphing calculator handle all of this for us. I'm going to do this problem mostly there. So let's see. I know that the first racer, Kimberly, is going at the rate of 2.3 to the x power times the sine of x over 2, like that. And I know that she is going to have the average of 16.102. And this is over the course of the first 6 hours of the race. So 0 to maybe 30, that'll show us everything right there. We'll push graph. So here is Kimberly's velocity doing what it does. We found the average velocity to be 16 point something. And that's going to happen, here's the horizontal line coming through right there. So the intersection appears to be, enter. The intersection appears to be at 3.34. So Kimberly, it's happening at x equals 3.342. Now Virag is going to be a little more complicated because his graph is a graph of distance, 20x plus sine of 2 sine of x, like that. And his average is going to be a slope. His average is 19.907, But we need to put an x after this since it's going to be a horizontal line. It's going to be a slope. So what we should see here, oh, the graph might not work for us. Hang on, let's second quit. Might need to adjust our y-axis here. Let's take y up to like 200. And even then, that might not do the trick. So here's his actual distance traveled over the entire race. And then here's the actual velocity. Man, that doesn't really fit either. Ah, geez, it's really hard to see when this is going to fit. You know, I'm not going to worry about this problem. I guess I'm out of time. I don't even heard the bell ring, but my third hour is going to come in here. This is a cool problem to leave off on, but I'm not going to worry about this. I'm not going to assign part C of this, or I'm not going to assign the next problem either, 743. So I'll make the edits there. Anyway, thanks for making it to this video. You guys are awesome. I'll see you in the next one.